Let's try to solve this question over here. A mummy in the arid island of southern Peru has a carbon-14 activity per gram of carbon that is 78.5% of the activity present initially. So when we talk about mummy, we're talking about a mummified corpse, which you usually find it in from ancient times. Okay, so this one is found in southern Peru. And if we extract the carbon-14 from this mummy, okay, let's say we extract a gram of it and we study the kind of activity that we find from this carbon-14 sample from the mummy, we find that the activity is actually less than the activity of the carbon-14 that are present initially. Okay, how do you obtain the activity of a carbon-14 present initially? Maybe you can get a fresh piece of wood, extract 1 gram of carbon-14 from it and study its activity. Okay, so let's say you have a piece of fresh wood and then you have 1 gram of carbon-14 that you obtain from fresh wood. You have 1 gram of carbon-14 that you obtain from mummy. Okay, so from this statement, it says that the mummy, the activity of the carbon-14 from the mummy is 0.785 of the activity that we found in a piece of fresh wood carbon-14. Okay, why is it so, right? It's because when we talk about a fresh piece of wood or fresh corpse, maybe, okay, a corpse that just died, okay, the moment they died, they no longer breathe, they no longer eat, they no longer have any living processes happening in them. So if you are talking about a living animal, let's say a living animal that's just died, the moment they died, they stop eating, breathing, and any living processes. That stop the process of us having any intake of carbon. Okay, the moment we eat, we are refueling ourselves with some ingredients, let's say bread, or let's say meat. Okay, those kind of bread, meat, if you break them down, there's a lot of carbons in it. Okay, so some are the common carbon-12 that we see, some are the radioactive carbon-14 that we consume as well. So when we are consuming food, we are having intake of carbons. So intake of carbons also include these kind of intake of radioactive carbon-14. Okay, so even though this carbon-14 in our body does decay, but we are replenishing them through the process of eating. So this process of eating, we increase the number of radioactive nuclei so that it reach a stable value. Okay, the process of us defecating maybe will decrease the number of carbon atom, but the process of us eating will increase back the number of carbon-14 atoms, and of course the carbon-14 atoms will also decay to other radioactive nuclei, but we keep it at a constant level because there's living processes that's happening throughout when we are living. Okay, so when you are living, the number of carbon-14 atoms it's not changing with time, so therefore we can say there's a certain activity that happens, okay, when you have this amount of carbon-14 atom radioactive nuclei. Okay, but the moment when you die, the moment you get mummified, that means by the Egyptian king or the Peruvian king maybe died, and that's the moment they stop having any intake of food, right? So when they stop having any intake of food, they also stop defecate as well, of course. So what can only happen is there's no more increase of carbon through eating. Okay, there's no more breathing, there's no more eating process, so the number of carbon-14 atoms can never increase. But even though the person has already died, has already been mummified, the carbon-14 will still continue to experience decay. So that means by carbon-14 can only decrease from the moment you die. It can never increase because there's no process to replenish the carbon-14 atom. So that means if you are living, the number of carbon-14 atoms in your body should actually remain around the same level. But the moment you die, the moment you stop eating, that's the moment where the number of carbon-14 atoms in your body decline. Why does it decline? Because naturally your carbon-14 atoms will undergo decay. So the number of carbon-14s will decline. So as it declines, the activity of the carbon-14 atoms inside the mummified body should also decline, because A is equal to lambda n, right? This equation over here. So if your number of carbon-14 in your body decline due to decay, the activity should also decline as well. So that's why they say that the activity per gram that you find in the mummy is less than the activity of the carbon-14 atoms that you find in a fresh piece of wood, let's say. Okay, it declines because the number of radioactive nuclei, the carbon-14 radioactive nuclei, has already decreased the moment they died. Okay, so this might take a bit of time for you to digest, but the idea is if you start at t is equal to 0, means by you just die, you have a certain amount of activity, okay, which is A naught. But as time goes on, okay, as time goes on, mummified already, left there, okay, at certain time later, which we are interested to know, discovered by present time human, okay, your activity now, it's only 0.785 of the initial activity when you die, okay, when the mummy died. Okay, why is it A naught is equivalent to the activity present initially? Because activity present initially means by it's the activity of a present living thing. Okay, the activity of a present living thing will be the same as the activity of the mummy the moment it just died. Okay, so A naught over here will be same. A naught over here, it represents the initial activity of the carbon-14 in the mummy when it just died, but it is equivalent to the activity present initially in any living things. Okay, because the moment the mummy just died, it's a moment it transitioned from being a living thing to a dead thing. Okay, and so you can equate the activity at that moment for the mummy to be the activity of any carbon-14 living organism, any living organisms that we have in at present time, which are living. Okay, it might get a bit, it may make things a bit too complicated, but if you want to discuss it further, you can talk to me. Okay, so basically this is the idea over here, but because we are interested in carbon-14, for carbon-14 what you know is that it has a half-life of 5,730 years. Okay, so this is a fixed value. Every single radioactive nuclei, they have their own half-life, they have their own decay constant. Okay, it is a defining characteristics for every radioactive nuclei. You have cobalt, which has a shorter time. You have uranium, which has a much longer time. Every single radioactive nuclei, they have their own half-life, they have their own decay constant. Okay, so right now we know that this is we are talking about activity changing from initial value to a final value. So this is related to how you determine how does the activity change with time. So we are going to use this equation. A is equals to A naught E negative lambda T. So this one, they give you an activity per gram. So activity per gram, you can think of it to be equivalent to activity, because that's the idea is you take 1 gram of carbon-14 from present time and you get 1 gram of carbon-14 from a mummy that you discovered. Okay, so they are both 1 gram of carbon-14, so they are able to make comparison between them. Okay, even though they are different sample, you can make comparison between them because they are the same 1 gram of carbon-14. Okay, so when they say it's per gram, don't need to worry too much about it. It's just a way for us to be able to compare between the activity at present time and the activity of a mummified corpse after they have been discovered a long time later. Okay, so activity over here can change it to be 0.785 A naught, so maybe A naught as well, e to the power negative lambda t. So this is where you need to be careful. Lambda over here, you don't have lambda, you can obtain it from half-life. So half-life is equals to ln 2 divided by lambda. Okay, so half-life is in 5,730 years. So if you use half-life in the unit of years, your decay constant must be in the unit of per year. Okay, I write it in fraction. So this one should be in per year because 5730 is in years, right? So if you shift it to the denominator, then the year should become per year. Okay, so this is a lambda that we have. So if we put in lambda over here to be in the unit of per year, your time unit will have to be consistent between lambda and t, right? So if this one is per year, your time you need to substitute in year. Okay, or the answer that you get for time should be in the unit of year. Okay, so if you proceed to calculate in your calculator, you find the time here to be 2001, and the unit should be years because you need to keep the lambda and the t to be consistent in time unit. Okay, so that means by this mummy over here has already been left there for 2001 years. Only it has been discovered. Okay, once it has been discovered and we study the activity of the carbon-14 in it, we find that it is 0.785 or 78.5% of the carbon-14 atom of the carbon-14 activity that we find in present-day living organisms. So the amount of decrease in the activity actually is a good indication of how long has this particular organism died. Okay, so this kind of technology, we call it as carbon dating. Okay, radioactive carbon dating, something like that. Okay, but it tells you the age of a particular died living organism from the activity of the carbon-14 in the body itself. So that's it for this question. Thank you very much.